Wait, I was mute. Oh, um, thanks for pointing that out. I didn't know that. That was actually very stupid of me. Let me just check if it's working now at least. Okay, I'll start from the beginning then. Basically, we're doing a number theory speed run where we're just trying to solve some questions from number theory. We already did multiples and now we're finishing divisors. We're just like doing it based on how many we feel is right. There's no exact like way I'm trying to figure out how many to do, but just a few questions. Then for the later ones, I'll just go until blue or green, depending on how much time I have. But like right now, for the first three, I'm just going to do a few random questions. So yeah, I was muted until now. So this is a I should have really checked that first, but okay. Plus one and plus 67. So we can do 2x. So we'll add 23, right? So we get either 24, 60. No, 67 plus 23 is 90, or we get negative 1. So 22, or we get 23. So negative 44. I think that's right. 1 second. Yeah. Then we obviously divide it. So we get 12, 45, 11, or negative 22. That becomes 46. So the answer to this should be 46 then. Okay, now we're at 98. So I think that's enough. That's like even higher than the last one. We'll do just one or two of these. This one will be, you don't need to test 31. You need to test 29. That's the last one you need to test. Okay. Goldbach's conjecture states that every even every even number greater than 2 can be expressed as the sum of two prime numbers. For example, this. Okay. How many ordered pairs? Okay, it's only two numbers. They'll both be odd so that they can add up like that. They have to add up to 60. Now, I don't really know any shortcuts for this. I think you just have to manually do it. Right, so we'll begin with 3, 5. We'll go until half. So we'll go until 29. 3, 5, 7, 11, 13, 17, 19, 23. And then after 23, it's just 29. So this obviously goes with 31. This goes with 37. This goes with 41. This goes with 43. This goes with 47. This goes with 49. This goes with 53. This goes with 55. This goes with 57. So this is out of the question. This is out. This is out. This works. This works. This works. All the other three works. So that's a total of 6. Yeah. Okay, wait. How many ordered pairs? Okay, again, another silly mistake by me. Since it's ordered pairs, I think that means you have to like take into account which one is first. So it'll just be this. 6 times 2, so 12. Okay, good. The digits of a two-digit number AB are reversed to form a second two-digit number, and the lesser of the two-digit numbers is subtracted from the greatest. What prime number must be a factor of the difference if A is not equal to B? Okay, this should be a one to answer like very easily, but basically, so let's say we've got 10A plus B minus 10B plus A. This is 9, right? Oh wait, no, never mind. So this gives us 11A minus 9B, unless I'm wrong. Oh no, it is 9A minus 9B. So it'll be 9 for this. But what prime number must be a factor? Then it has to be 3 because 3 is the prime there. Okay, 97. Again, that's fine. Wait, how are we doing so badly here if we've done 14? 97, 98, 97. Let's do a few remainder ones. Let's just get to blue over here. Joe is thinking of a positive integer less than 100. It is 1 less than a multiple of 8. And it is 3 less than a multiple of 7. What is the greatest possible integer Joe could be thinking of? Okay, not sure how to do this actually. 90. I think it's 95, right? 95. I don't know why though. I just like I think you just have to okay, anyway, ignore that. Basically we need n to be like have nothing in common with 99. So it's with zeros less than that. So it'll go from 1 to 98, which means that 98 terms. Let me scroll down a bit again. So there'll be um 98 terms in total, and you subtract off the number of divisors of 99. So the number of how do you write it? Is it n of 99? Might be wrong. But then remember that n of 99 is including 99 and wait, is including 99, which we aren't supposed to do. So we'll add one. So it becomes 99 minus n of 99. 99 is just 3 squared times 11. So this gives you 3 times 2, 6. So it should be 93, but could be wrong. Okay, it's wrong again. So this is actually pretty bad. How is 99 wrong? It's 3 squared. Oh, wait. It's any multiple of them as well. Doesn't just have to be like one of those. It can also be a multiple. So it's how many multiples of 3 are there? So, okay, it's going to be 98 minus multiples of 3 from 1 until 98 minus that minus the number of multiples of 11 that you have over there and any intersections. Like, are there any in common between them? Uh, you add that. So you'll add basically 33 and 66. So that's 2, right? You're subtracting all the multiples of 3 from that. So that will begin at 3 and end at 96. Divided all by 3, you get 32. Similarly with 11, you start here and you end there, which gives you 8. So it's minus 32 minus 8, and there are 2 that intersect. So in the end, it should become 98 plus 2, right? Because they're, wait, 1 second. Yeah, 98 plus 200 minus 40 is 60. So that should be right, hopefully. Okay, good. What is the least? Oh, wait, they made us skip it, I think. 1 second. Yeah, we have to go back there. They ended automatically at green, and we want more than green. What is the smallest prime divisor of 5 to the 23rd plus 7 to the 17th? So I don't know about this one. Well, they'll both be odd numbers. Oh, okay, it's 2 because they're both going to be odd. When you add them up, they'll be even. So you have to do that. Okay, you just mastered. You have mastered. Okay, so then we go here. Okay. What is the least positive integer divisible by each of the first 8 positive integers? Least positive integer divisible by each. So 1 times 2 times 3 times 4 times 5 times 6 times 7 times 2 cubed 8 times 9. Sorry, we how many is it? Just the first 8, right? Yeah. Now we can ignore this 2. We can ignore this 2 squared. We can ignore this 2 because we've got a 2 cubed. Similarly, we can ignore one of these. So now we've just got 8 times 5 times 21. So 40 times 21, which is 840. Okay, we passed that one as well. So let's. Okay, wait. Least common multiple. So we need to go there now. Billy and Bobby each selected a positive integer less than 200. Billy's number is a multiple of 18 and Bobby's is a multiple of 24. What's the probability that they selected the same number? Okay, so how many are there in total? Multiples of 18 or 24. So multiples of 18 and from where? So less than 200. So from 0 to 200, wait, they have to be positive integers, right? So from 1 until 199 basically. Um, so the number of 18 plus the number of 24 minus the number that are just 18 and 24. That's how many there are in total. And we just do this. So number 18 and 24 divided. This is what we're looking for basically. That should be our answer. Billy and Bobby each selectable. Yeah, okay. So I think that's right. How many are there like multiples of 18? So you begin with 18 and you can go until 198. If you divide this, you get 1 until 11. So that's 11. How many are there of 24? You start at 24, obviously. You go until 96, 192. And 192 is going to be 8 times that. So it's 1 to 8, which means this is 8. This is 11. How many are there now that are multiples of 18 and 24? So that means you have to be a multiple of, you have to be a multiple of, so what is 18? 18 is just 2 times 3 squared. And meanwhile, this is 2 cubed times 3. So you'll skip this and skip this. You just have 2 cubed times 3 squared, which is equal to 72. And there are two, obviously, there are two multiples of 72 over here. 72 and 144. So that's 2. So 11 plus 8 minus 2. This will give us what? 19. So 17. 2 over 17. Okay. What? Oh, so that, wait, what's the worry that they selected the same number? Not that the, wait, what have I done here? I've done, what is the probability that the numbers that they have are basically both multiples of, what's the probability that they both selected? Well, basically in total they're going to be these many. They're going to be these many numbers. So the probability that they both select, okay, wait. So we can say that the probability that one of them selects one of them is going to be 2 out of 17, right? The probability that Millie or whatever, sorry, Billy will select one of those two numbers, it's going to be 2 out of 17, right? 11 plus 8 is 19 minus 2, 17, 2 over 17. So the probability that one of them chooses one of those numbers times the probability that the other one chooses that same number is going to be 2 over 289. Right now, I don't know, do we need to multiply that by 2 to account for the other case or no? I don't think so because, yeah, it shouldn't matter. So I'm guessing it's 2 over 289. No, it's wrong. Okay, let's see why. Hmm. Okay. Together they can pick 11 times 8. Where are you cutting 11 times 8? Let's see. 11 times. Oh, because of the number of multiples of 18, number of multiples of 24. Those many combinations. Okay, fine. And two of these involve them choosing the same thing. So it's 2 over 88, 1 over 44. Okay, makes sense. Find the least common multiple. Wait, what just happened? Shouldn't we go back there? No, I think we okay. Find the least common multiple of these two. 36 and 132. Um, so this is just 2 squared times 3 squared. This is, what is this? This is, so this is 2 times, what, 66. So it's going to be 2 squared times 3 times 11, right? Yeah. So when you're doing the least common multiple, you choose this one, and this one, right? So this will be 636 times 11, which is 396. So that should be the answer, 396. Okay. Uh, so also for a few weeks to lay eggs underground. The offspring spend several years underground as eggs and larvae before they emerge as adults. So basically, they're just asking for the LCM of all of those different numbers, right? Which is, and then add that to 2000. Yeah, wait. If they have life cycles of one, yeah, okay. So 2, 4, 30, and 70. 2, 4, 13, and 17. We want to find the LCM of that. 2, 4, 13, 17. First of all, the 2 doesn't matter because that's covered by the 4 already. 4 and 13, they're all prime numbers, or but like co-prime. So we just multiply them. 52 times 17. So 520 plus 350. So plus 364. So this becomes 884. So it'll become 2884. Unless I did something like wrong in there. Okay. Oh, wait. Which is an action which the adults have exactly three of the four. Why do I always mess this up? That will be 52. So 2052. I'm guessing. I didn't read it at all. Okay, so at least we got it right now. That's fine, but not good. Okay, now we're back to the Euclidean algorithm. Find the smallest possible, find the smallest positive integer n such that these two share a common factor greater than one. Um, what if we just like, okay, what if we plug in values and just kind of guess and check? Could that work? Oh no, never mind. This is the Euclidean algorithm. 9n minus 2. So 9n minus 2. And what's the other one? 7n plus 3. 7n plus 3. And we want the GCD. So 2. Yeah. Okay, so we can subtract this off once. GCD. So when we subtract 7n plus 3 from this, we get 2n minus 5. 7n plus 3. We can subtract 3 times this. When we subtract 3 times that, we get GCD of 2n minus 5 and n plus 15 plus 3. So it becomes n plus 18. And when you subtract this, you just get GCD of, um, well, we can subtract twice this then, I guess. So we basically get, when you subtract twice that, you get 41 and then n plus 18. So now over here, when you need to have them both be equal to 41, so it should be 23. Okay, good, finally. Well, this is negative 41, just to be clear, negative 41, but it's the same as 41, so that's why I did that. 9 and okay, I'm still very grateful that I pointed out that I was muted because that's actually pathetic. Okay, now we're on this over here, LCM GCD problem solving. And after this, we'll just promote these and then we'll have a nice streak of blues going on. So let's see. An 8-digit integer is formed by repeating a positive 4-digit integer. What is the greatest common divisor of all 8-digit integers of this form? So okay, this is a common-ish problem. So you have basically, it's not 1001. I think it's 10,001, right? I think at least, because then when you like if you multiply this by a 4-digit number, this will take up the first 4 digits. Wait, yeah, okay. So like if it's 5437, then you get 5437 times 5437 5437. That becomes your number. So it's just going to be this. Now, what are they asking? What is the? Oh, okay, yeah. I thought they were asking for a prime, which would make it a lot more complicated, but luckily no. How many integers m are there such that this is the case? And GCD of m and 100 is a single digit number. Okay, what are the? So we need a common divisor, right? Tens only common divisors that are one that are less than that, like single digit, are 1, 2, and 5. 1, 2, and 5. So I think instead of this, we can see which ones aren't. Like which ones are multiples of 2? Multiples of 2. Well, no, 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 no. 10 also has 4, right? So these are some divisors that 10 has. Besides that, 10's divisors include 4, right? Yeah, so there's 4, and then there's also, like, I guess 10. Sorry, what am I doing? There's 4, 10, 25, and then 100. Is that everything? Like, okay, if we list out all the divisors, it's 1, 2, 4, then it's 5, um, then it's 10, then it's 20, then it's 25, and then after 25, what is it? Then it's 50, and then it's 100. So you've got all of them listed. How many integers m are there from 1 to 99 basically? So from 1 to 99, which means that there are a total of 99 minus. Now, how many have GCD 4? How many have GCD 10? How many have GCD 20? How many have GCD 25? How many have GCD 50? None of them will have GCD 100 because that's impossible if it's from 1 to 99. So we just subtract out each of these. Luckily though, all the ones that have GCD of 20 will by definition have GCD will have a common factor of 4. So we can ignore this. Similarly, the ones that are multiples of 10 will be multiples of, okay, we can also ignore 50 because that will be covered by 25, right? Then what about 10? I don't know about 10, right? Because so 10 is 2 times 5, right? So let's just figure out all of them manually, okay? So 25, then you've got 50, then you've got 75. So this gives you 3. 10, you've just got, like, how many will you have? It's easy to figure out. With 4, you have, so, oh wait, actually, yeah, this is a bit interesting. There's a more work to be done here. Luckily, 4 won't intersect any of these, but 4 will be, how many will there be? It will go from 4 until 96, which means, so this is with 25. With 4, there'll be 24 such numbers, and with 10, you'll go from 10 to 90 for 9 such numbers. Now, between 4 and 10, how many common things are there? There's going to be 20, so it's just all multiples of 20 basically. So that goes from 20 until 80, which means I have 4. So over here, there are 4. There's nothing between 4 and 25. Between 25 and 10, there's just 50. So that's just one. And are there any that are in common with all of them? If that's the case, then you add those. But there aren't any, right? So we can just do 99 minus. We add up 3, 24, and 9, which gives us 36. Then we subtract off 5. Okay, that was a lot. This becomes 33, 36, so 31 minus 31, which becomes 68. I hope. Okay, it's wrong because I'm an idiot. Because 4 actually does work. Okay, so 4 also does work. I just forgot about that. Um, Wait, that makes our work so much easier actually. I don't know. So 4 does work. Instead, we can just focus on, so 10 took care of 20, 25 took care of 50. So we just ignore all the 4 ones. Those are all fine. What we care about are the 10s and the, so are the 10 and the 25. So that's 3 plus 4 minus 1. Sorry, 3 plus 9, 12 minus 1, so minus 11, which means it becomes 88. I hope. So let's see, 88. Great, we got it. You just passed this, so we'll go back there. We want to keep doing it. Okay, now this is a bit, yeah, kind of hard. I don't know. Basically, B is equal to, okay, so I'm sure there's some properties here that can make our work easier, but I don't know them. I don't know them. So, um, let's see. A, B, and C. We can at least write some stuff down though. A, B is 168. Let's just write it down here. So GCD of AB is equal to 168. Similarly, GCD of, I think they gave us A and C, and that was equal to 693 or something like that. Yeah, 693. And then they're asking us for GCD of B and C. And they're asking us, I think, for the minimum value. Yeah, minimum. Okay, let's take a look at that. So A is equal to 693 times some C, right? 693. Not C, I shouldn't take C because that's already a variable, but it's equal to, basically it's got in it. Wait, do we even care actually? I don't think it really matters unless, yeah, wait, we'll do this. So A is equal to 168. How do you write that out? You write that as 84 times 2. This is 2 squared times 3, so that's 12 times 7. So this is 2 cubed times 3 times 7 times x. A is also equal to, now from here we can divide it by 9, but I don't know what that is immediately, so let's just divide it by 3 first. That will give us 231. Divide this by 3 again, that gives us 80 minus 3, so that gives you 77. So that means that there's a 7. Oh wait, this is not hard at all. 7 times 3, and then that's 3 squared. Okay, so 9 times 7, 63 times 11. Perfect. 3 squared times 7 times 11. So this tells us that there's, okay, if there were an 11 in B, wait, so this is with C. We know that A is then 2 cubed times 3 squared times 7 times 11 times some, like whatever, y. Or if this is, I'll call that y, I'll call this z. Okay, good. So now we know this, right? We also know that C is equal to, like, something like this, and B is equal to something of this form. One second. So C and by the same logic which we used for A, C is of this form, B is of this form. But we know that they can't have anything in um so okay, we want to now minimize it, right? So we know that there has to be 1 7. We know that there has to be a 3, like minimum 1 3. We know that there isn't an 11 in A, right? I mean in B. If there was an 11 in B, there's also an 11 in A. We know that already because this is A. So this would not be 2. So we know that there is no 11. Then for 2 cubed, if there was any power of 2 in C, then A and C would not give us 693. This is also impossible. So to minimize it, we have to take the 3 from here. We have to take a 7. We have to take either 3 or 3 squared. To minimize it, we'll take 3. So 3 and 7, 21. Yeah, 21. And so besides that, X and Y, we'll just make like whatever, I don't know. Just 21 should be fine. I think there was a much faster way for this, so not sure, but whatever. Last question to get to the blue level. The greatest common divisor of two integers is x plus 2, and the least common multiple is x times x plus 2. If one of the integers is 24, what is the smallest possible value of the other one? We know that the least common multiple times the greatest common divisor is the product of the two. So we know that x times x plus 2 squared is equal to 24 times something. Is equal to 24y. And what do we want? We want the minimum value, right? The smallest possible value. Remember though that, wait, x is a positive integer, so it has to be at least 3. Y is greater than or equal to 3 because otherwise, because we know that the GCF is, the GCD is x plus 2 where x is a positive integer, so the minimum value it can be is 3. So there has to be a 3 in it. And so if y is at least 3, let's look at the prime factorization. So 24 is 2 cubed times 3, and then when you multiply it by y, that becomes 3 times x, or like some x type of thing. So to make this work the best way we can, we'll have x plus 2, we'll have this be 6 squared. X plus 2 squared is 6 squared, which gives us x equals 4. And again, I used x over here, so call this asterisk instead, or whatever. So x is 4, that gives us 6 squared. We've got this here, so then that just has to be 2, which means y has to be 6. Yeah. How many perfect squares does, okay, we master that. How many perfect square factors does this number have? How do we do that again? We basically, yeah, okay. So, okay. How many perfect square factors does this number have? 46, 656. 46, 656. It's such a big number though, so I don't even know what to do here. We can take out a 4, right? That will give us, what will that give us? Will that even make it much easier for us? Can we take out something bigger than a 4? Like what about an 8? 640 works 656. So we can take out an 8. What about a 16? Let's just divide by 8 for now. That will make it a bit easier at least. Okay, 5, 8, 3, 2. We've got 8 times that. So that's fine. Now over here again 832. We can again take out an 8, can't we? Yeah, we can. So 5832. How many go into 58? So it'll be like what, 7. So 7 minus 56, 2, pull down 3, that will give you 2 minus 729, right? Because it becomes 23 minus 16, 729. Okay. And now, luckily, at least we know that 729 is 9 cubed. So it's basically 8 squared times 9 cubed, which means this is 2 to the 6th times 3 to the 6th. How many perfect squares do you have here? So you can choose to either have 2 to the 0th, 2 squared, 2 to the 4th, or 2 to the 6th. Similarly, you can have 3 to the 0th, 3 to the 2nd, 3 to the 4th, 3 to the 6th. This gives you 4, this gives you 4. Multiply them together and it's 16. Okay, so that took, wait. Okay, perfect square factors. Good. Positive integer n is nice if there's a, what happened here? Positive integer n is nice if there's a positive integer m with exactly 4 positive divisors, including 1 and m, such that the sum of the 4 divisors is equal to n. Find the sum of all the nice numbers in the set 20, 10, 20, 11, 20, 14. Okay. No, not this question isn't nice. Basically, you need including 1 and m. So you're going to need m to be like greater than half. I don't even know how to start this. Um, it's not an easy one. Wait. I'm sure there's some trick for it, but it just seems like, and it's also such a small set. So, okay. Well, think about it. If it's an odd number, then won't all of its things be odd? Like all of its divisors will have to be odd. Oh wait, never mind, never mind. That doesn't matter. So okay, if it's an odd number, there are exactly 4 positive divisors. M. Okay, wait. Let's write this stuff down. So you have 1. You have like let's say x, y, and then you have m. If m is even, and then if m is odd. Okay, if m is odd, that makes our work easy. Then the sum of then all of them will have to be odd, right? Uh, all of them will have to be odd, which means that the sum is even. So the sum is even. Over here, the sum is even, which means that n is even, or maybe lowercase n. I don't know. Meanwhile, here, if m is even, m is obviously even. These can both be like they can be even even or odd even. So that doesn't help us. That means that the sum can be either, yeah, sum is odd, sum is even. They're both possible, which means n is odd or even. So both work here. So that doesn't help us. But doesn't that, okay, that tells us if the number is odd, then m has to be even, right? If the number is odd. So if n is odd, m is even. Has to be even so that you can get this setup. So, sorry, so that you can get this. Wait, no, so you can get this setup. Odd, 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 plus even. Right. And there are a lot of odd numbers here. Okay, now we also need that the sum of all the four divisors is equal to n. I don't know how you can do anything with that, right? Because you need basically 1 plus, let's see what we can do. Xy is equal to m, so xym, no, x plus y plus m. We know that. We know that x is just m over y, so that's m over y plus m over x plus m is equal to n minus 1. I don't know how this is helping us, but let's just try it. We can divide. Wait, can you still see all this? No, you can't. Let's zoom out a bit. 1 second. I just want to make sure you can see the screen. Okay. You can divide it by m. That gives you 1 over y plus 1 over x plus 1 is equal to n minus 1 over m. Then this is just x plus y over xy and then plus xy is equal to n minus 1 over m. I don't think this will help us at all. Yeah, this is just been a useless thing. Oh, just so you can see, what I did was this. But there's really no point. It's completely useless. This stuff over here. Alright. Actually, I'm completely stuck on this. I don't know. I have no idea here. We can probably take a guess if we have to, but I don't see the point of that either. What if there are like none? But I don't think they'd give that. I think there'd be at least like one or two. Like you have to figure out and then check. But how would you go around checking this anyway? It's not exact. Okay, wait. Oh, if if M has exactly four positive divisors, that would mean that if it said like five positive divisors, that would be interesting. That would mean that M is a perfect square or something, right? But that's not the case either. If it has exactly four positive divisors, that means it's just equal to two numbers multiplied by each other. I don't know. I'm just going to guess zero. That's wrong. And I'll guess zero again. Okay, fine. Let's just guess like 2019. Okay. Okay, first one makes sense. First time makes sense. So p cubed. Okay, I didn't think of that. Or p times q. So p times q is what I was thinking of, but I didn't really do anything with that. No primes work. 11 is too little and 13 is too high for that range. Yeah, they took the sum and then they checked the two numbers and they found that no prime p gives a value that works. So you have to have m equals p times q. Then the sum is this, which we can factor as okay, okay. So that I didn't think of. But first suppose that one of p and q equals 2 without loss of generality, let p equal to. So then this is equal to 3 times 1 plus q. Since q is not equal to p is equal to 2, we see that q is odd and so this is even. Okay, so they just use process of elimination here. So Q and P cannot be 2. Right? I think that's how they figure out. First was that one of P and Q equals 2 without loss of generality. The reason they did that was so that you can have an odd thing, which makes sense. Right? That's so we see that Q is odd. Q is not equal to P because otherwise you just have um that wouldn't work. That would just be of the form P squared then, which will only have 3. 1 plus Q is even, so it's divisible by 6. Okay, so they found that that's divisible by 6. Makes sense. 2010 or 2016. Okay. Trying both cases, we see that neither of them work because just by plugging in the values. So that is a lot of calculation, but fine. First one would give you Q is, yeah, whatever. So done. If neither P nor Q equals 4, then both are odd primes. So it's a product of two even numbers, which is divisible by 4. So again, then it's just 2012 and 2016. 2012 is 2 squared times 503. So the only way to write it as a product of two even positive integers is this. But you can't have 2 because then it'll become P will be 1 or Q will, like one of them will be 1. And so 2016 does work because it's um 4 times 504. Okay, yeah, yeah. Both 3 and 503 are prime, so 2016 is nice. Okay, so that was a lot of work though. There's a lot of calculation involved there. How many even positive factors does n have? So basically just like remove one of the power multiples of 2 in there, one of the powers of 2. So it's 2 squared times 3 squared times 5. So it's 2 times 3 times 3, 9, 18. What is the smallest positive integer n with exactly 14 positive divisors? Okay, so to have 14, um, it's either of the form n to the 15th, which obviously isn't. Okay, first of all, what is 14? 14 is 1 times 14, or 14 is 2 times 7. That's it. If you do 1 times 14, um, like it'll be of the form n to the 13th. This will meanwhile be of the form p times q to the 6th. To minimize this, you take q equals 2, right? That'll be the best. And then p equals 3. 2 to the 6th is 64. Multiplied by 3, you get 192. Okay, done. Find the sum of positive. Find the number of positive divisors of 9 factorial. So what is 9 factorial? That it's a big number, right? So it's going to be 1 times 2 times 3. This time we just write it all out. 2 squared times, so 1 2 3 4 5. 2 times 3, that's 6, that's 7, 8, 9. That's it. Now we just put them all together. So we've got 1, that doesn't even matter. 2, so this is the first power, second power. So you add that up to 3, 4, 7. So 2 to the 7th times 3. 3 to the first power, first power again. So 2 and then 3, 4. So 3 to the 4th times 5 times 7. So that becomes 8 times 5 times 2 times 2. That becomes 10. So 8160, which is a lot. Now done with divisor arithmetic. Let A be the product of the divisors of 42. So it'll be 42 to the power of, and how many divisors does 42 have? Like, I mean, yeah, how many divisors does 42 have? So 42 is equal to 2 times 3, so 6 times 7. So that gives you 2, but it gives you 2 times 2 times 2, which is 8. So you have 8. 1 second. So it'll be 42 to the 8 over 2, which is 42 to the fourth. Because of that, then everything will go to the fourth power here. 4, 4, 4. So it's 5 times 5 times 5, 125. Okay, wrong again. Distinct. Oh god. Distinct prime factors. That should just be 3 then, right? I don't read any of this stuff properly. But let me check actually. I don't want to get it wrong again. Yeah, that seems right. 3. Should be 3. Okay. The sum of the positive divisors of a positive integer of the form this is equal to 600. What is I plus j? Okay, so there's obviously some trick to this, right? Because some, like, that's not something you want to calculate manually. But so basically you'll have 1 plus, you'll have plus 2 plus 3. How many factors will you have in total? Right, you can figure that out. That will be I plus 1 times j plus 1. You'll have an odd factor, even factor, odd factor. Wait. So how many even factors will you have? You can figure that out as well, right? That should be easy enough. So I minus 1 times. Wait a minute. No, I times j plus 1 is the number of even factors. Wait, this is not. This is too hard. Let's see. So obviously you'll have a lot of multiples of. You'll have a lot of multiples of 2i, right? Like, so so okay, this makes sense now. I think so. You'll have 1 plus 2 plus 3 plus 4 plus 6, right? Plus 9. But then you'll have plus 12. You could also have a plus 8 in the middle, by the way, right? So then you have plus 9, then you have plus 12, then you have plus 15, then you have plus 16 potentially. So the important thing is that this is even, 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 even. Oh no, you won't even have 15 because that's not possible, right? So you won't have that. You'll have 16 instead. Then maybe you can have 18. Then you'll have, you know, it's multiples of 6. So then next one will be 24. Um, then maybe you can have 27. So look at how many even ones there are, right? Even, 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 even. That means that there must be. Now look at the odd ones left. These have to add up to an even number in the end, right? Because it's 600. If you subtract all the evens from it, be left with an even number. And this is basically 3 to the I. There are 3 to the I plus 1 of these, right? There are 3 to the I plus 1. If I is just 1, so then it's um 3 to the I. So it's 2 times whatever, 3. So there'll be 3 and there'll be 1. So basically 3 to the I plus 1. And I plus 1 is even. Right? Sorry, if it's of the form 3 to I, um, you need it. So 3 to the I, right? So you need I plus 1 to be even. That's basically what you have. If I plus 1 is even, then what do we have? We have, so you obviously need a big-ish number. Like, it can't be a small number like that. And at the same time, uh, there have to be, at least, what's the maximum value you can go and get, right? like, okay, if you just add up, like, even if you just add up the threes, it's a geometric series, right? So it'll be 3 to the I plus 1. Um, 1 second, what is it? Minus 1 over 2, right? That's what it'll be. What it will be. And so we want this to be less than 600, which means we want 3 to the I plus 1 to be less than 1200, 1201. Give me 1 minute, please. I'm back now. Yeah, let's continue. All good. I think I'm unmuted and everything. Good. We need this to be true, in which case I is. We need an even power, right? 3 to the. So what is 3 to the fourth? This is equal to 981. 3 to the sixth is going to be 9 times that. So that'll be 729. The next one will be way too much, right? And 3 to the sixth. 3 to the sixth. If you plug this in over here. Wait, what am I doing? I plus 1 has to be even. Yeah, so this works, but the next one, 3 to the 8th, will not work because that will just be too much. So the maximum we can have is I equals 5. Right? That's the maximum we can have. Besides this, what all do we have? We have, so I equals 5 works, I equals 3 works. Let's see if there's anything else in the question. Uh, okay. Can we do a similar thing with 2? I don't think so. I don't think we can right now. But and then I guess I equals 1 is also possible, but it's not, probably not too likely. Yeah, wait, I equals 1 won't happen, I think. Um, oh, wait, was this J? Yeah, all of this is supposed to be J, so we'll just flip it. So these are the three possibilities. Now let's see. We also want to make sure that obviously, you know, um, 2 cannot be 0, right? 2, it has to be, there has to be at least 1, 2, because otherwise, otherwise everything will be done by the I equals 5. Right? Like you need at least some 2 there so that all these extra terms come in as well. If you don't do that, nothing will come in, and that will be bad. That will mean that you have to get 600 just with the terms that you have here, which is impossible because this uh, this is not possible, right? They can't be equal. So it has to be less than that instead. Which means it'll be at least, so I is equal to at least 1. J is, sorry, then this is 3. So I is equal to 1, 3. J is equal to 1, 3, or 5. Let's see. If 3, what is 3 to the fifth power again? Let's check. 243. If you multiply this by 2, I think it's already out of hand. Right? That will just be, too much. 243, and then you're multiplying it by 2. So that becomes 486. 3 to the fifth. So there'll be a 3 to the fourth. There'll be an 81 over there. There'll be 2 times 81. So that's way too much. So that means that it's not going to be 5. Right? What about 3? I think 3 can work, but I don't know that. Yeah, I think it'll have to be 3 because 1, again, there must be some reason that 1 itself won't work. I'm guessing because, so I want to guess 3. Oh wait, no, then we have to find out I anyway. So we need to figure both of them out. Let's see that then. Let's see. We've gotten a bit far. We've narrowed it down. We know that J is equal to 1 or 3. What if we now see what else we can do? Let's list out a few terms, right? Like, let's say, what if 2 is just equal to, like, it's just 2. It's 2 to the first power. Then we have 1, 2, then we have 3, then we have 6, then we have 9, then we have 18, then we have 27, then we have 27 times 2, that's 54, and so on. Okay, yeah. This gives us the possibility for 2 I equals 1 and and 3 j equals 3. This is obviously way too little, right? And it would be even worse if it is just j equals 1. So it's not this, but we know that, okay, wait, maybe we can just knock out j equals 1 completely, right? Because that would mean that you just have 1, 2, 3, then you have 4, then you have 6, right? 2 times 3, then you have 8, 2 cubed, then you have 4 times 3, that's 12. Then you have, next one you'll have is 16, then you'll have 3 times 8. Sorry, yeah, 3 times 8, 24. There's a pattern that I'm noticing here, and I think you'll notice it too. What have we done here? We've taken I equals 2, right? So I equals 2 and j equals 3 means 27 times 4 for 108, which seems like perfect now, right? Because it'll go on until 108. Notice that this is 10, this is 20, this is 30. So by the time, we start to approach that, and then, yeah, this is being multiplied by 2 each time. So we can, continue it. Now it will become 48. No, what the hell? This is 40. Sorry, this is 40, which means the next one will then be 80. Okay, so I know this has taken a very long time, but I just want to make sure I get this question done, no matter what. 40. Then the next one will be 80, right? And 24. We go on to 108. So it'll be 24. This will be with what? This will be 32 and 48. Then we'll have 32 times 2. So then we'll have, and aren't we missing anything? No, we're not. Yeah, then the next one we have is just going to be, so we had 1632. The next one will be 64 and what? And I think that's it. But that's impossible. It can't go on this long because we stopped it at 2 equals 2. Okay, here we're just going for 2 to the I times 3 cubed. This is what we're doing right now, right? It's not 2 squared 3 cubed. It's not that, which is what I was saying before. So it's not going to stop over here. It'll keep going until we decide to make it stop, which will happen when, so you got a 64 now. What will the next term here be? 96, which means this will be 160. Yeah, obviously 160. I think then we can add one more, right? Because here what do we have? Here we've got a sum of 6. This is adding up nicely. 96. I think now we do have to cut it out though, right? Because 96 is 3 times 32, 2 to the 5th. This is already gone to 2 to the 6th. Sorry, 2 to the 6th power. So I guess after that then we have to slowly, wait, no, over here we just done j equals 1. Yeah, that's what we done. So 2 to the 6th and j equals 1. So the next term here, then I guess we'll do one more term because this doesn't seem like it's anywhere near 600 yet. 240. Well, wait, 240, 280, 300, and so on. Yeah, so this probably won't work. Um, right, we've done 2 to the 6th, so 64 times 3, 192. Yeah, I think we're done then. This is wrong. Right, this won't work either. The point is, yeah, well, that's the logic though. If you add one more, it'll be too much. Right, here we've done, what we've done here is 3. 3 to the first power, 2 to the I, 3 to the first. That doesn't work. Which means that the only option left is this. We have to have j equals 3. And now when it's j equals 3, then I think we just plug in different values and see. And we don't even really need to do that. We can just check, right? Um, we can use the geometric series of just 6 cubed. Hey, that will give us 1, 6, 6 squared, 6 cubed. And obviously this is way too little, right? That will be 6 to the 4th minus 1 over 2, which is, wait, this is, I don't think we're doing it right though. Yeah, over here, so 6 cubed, let's just take a look. I don't think we can do that, but 6 cubed will be 1, 2, then there'll be 3, then there'll be 4, then there'll be 6, then there'll be 8, then there'll be 9, then there'll be a 12 as well, I guess. There'll be a 16, there'll be an 18, and so on. I don't know how to really simplify this, but basically it'll keep going like this, right? And have we reached 216 yet? Like when you multiply them, have we reached 216 over there? Yes, we have, right? 8 times 18 is, no, nowhere near. 12 times 18 is 216, I think. Yeah, okay. So then what is this 16 doing over here? We can't have that. There is no 16, right? Because 16 is 2 to the 4th, which we haven't allowed over here. Okay, not bad, not bad then. 6 cubed. So it's like basically 2 cubed times 3 cubed is equal to this. 1, 2, 3, 4 works, 6 works, 8 does work, 9 works, 12 works, and then I think 13 doesn't work, 14 doesn't work, 15 obviously doesn't work, 16 doesn't work, 17, and then 18. Yeah, perfect. 18. So now 9. What is 216 over 9? Come on. 20 plus 36. So 24, I think. Yeah, 24. Perfect. Then what is 216 over 8? So 27, I believe. Yeah, obviously that has to be the case. 16 then becomes 36, then it becomes 827. So that should be 54. Then it becomes 72. Then it becomes 108, and then it becomes 216. And I think this could be it, right? Because if you add these two up, you're already at uh yeah, you're over here. If you add these two, you get, what do you get? You get 324, right? Then these two will be about 100 more. 126. So that's already like 450. then what will these add up to? Sorry, what am I doing? This is 50, so 60, 87. This is another 30. Yeah, so they're getting pretty small now, but this is 10 plus this 27. So, what, 1 second. 17 plus 3 is 20 plus this. So, this is another 30. And then this becomes 3. Yeah, and so this is 60, 147, 150. All of this adds up to 150. And this adds up to 450. So, finally done. It's 6 cubed. Finally. Wait, I am actually stupid. I did it correctly, right? Didn't I do it correctly when I did 6 to the fourth minus 1? Instead of dividing it by 2, it should be divided by 5. And this would give you, well, wait, this gives you 1296 minus 1, 1295. Yeah, so this is wrong, but I thought it was 24, 240 plus 19. So this would be 259 or something, which is wrong, but it's still a good estimate because so if you add up this, if you add up this, and if you add up this and this, that would give you 259, right? Yeah, and that alone is like an estimate. It's like about half of the total. Anyway, here our answer is 2 cubed, 3 cubed. So I and J are both 3. So the answer is 6. And it shouldn't have taken that long at all. The sum of the divisors is equal to 1 plus 2 to the... Okay, that's a factorization which I didn't know yet. But that does make a lot of sense. So let it be. So they broke it up into cases and then they checked from there. Okay, I think we took way too long in the work here, but at least we got it right. Okay, so, okay, and last one now. The product of the positive integer divisors of a positive integer n. So, product of the positive integer divisors of a positive integer n is 729. Okay, so it's a number. Um, right, what about 9? I have a feeling it's 9 already because 9 has 3 squared. No, so it's not 9. What if I'm guessing then 27 potentially? Right, because this is 27 squared. 27 is equal to 3 cubed, which means it's got 4 divisors. So the number is 4, so it'll be 27 to the 4 over 2 equals 27 squared and 29. Okay, good. Good, good, good. So 27, done now. Thank God. Okay. This was guess and check, but um, let's just read the solution once. Since the divisors come in pairs, the product. Okay, so we know that formula. For example, if n is odd, then d minus 1 is. Okay, good. For example, okay, these are just examples. So summarize, we have found that the product is writing 729 as 3 to the 6th. Then we have, okay, yeah, so they did it the other way. We noticed that 729 is 27 squared. They noticed that it's 3 to the 6th. Then they did a more procedural approach, which we didn't. So 3 to the 12, 3 and 12, 9 and 6, and then they just saw when is the number of divisors the second coordinate and the number the first one, right? And so the only one that makes sense is 27 and 4. That's the only one that works. Anyway, we're done with that though now. And now, as you can see, we've done like how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 of our units now from the top are completely blue. There are a few more, there are two more. So 13 out of, so maybe like, I think almost half of number theory is just blue now. And I have to go. I have to go. So we'll continue this next time. It's been 1.5 hours now, which is a fair bit. We'll continue this later. So thank you for watching.